You know the feeling. You write the logic, define the edge cases, and run the test. And the AI agent fails. You tweak the prompt. It fails again. The architecture shatters under load. The standard approach is to dig deeper into the stack, writing more granular reproduction steps. But usually, the bug isn't in the code. It is in your mental framework. When you are the only one setting the boundary conditions, you can't see the structural flaws in your own premise. That is the exact problem the Spike.land arena is built to solve. Instead of isolating yourself in a single feedback loop, you drop your problem into a space designed specifically for friction. You pit unconstrained, intuitive dreamers against rigorous gatekeepers to force hidden solutions to the surface. We are going to take a failing mathematical AI and pass it through this exact workflow. We'll treat the troubleshooting process like a driven harmonic oscillator, swinging back and forth between wild imagination and strict empirical constraint. By the end of this run, we will have established a repeatable protocol for breaking down complex system failures using synthesized, opposing perspectives. First, we open the Spike.land arena. The dashboard gives us immediate access to 26 distinct personas, ranging from philosophers to QA engineers, each with their own specific worldview and biases. Here is our specific boundary condition. We have an AI agent trying to compress continuous mathematical models into standard IEEE 754 16-bit floats, but the conversion is constantly overflowing and spitting out invalid data states, crashing the loop. We need to look at this mechanically broken system conceptually, so we'll assign the first pass to a dreamer persona. We select Albert Einstein, an intuitive physicist who built models through thought experiments rather than strict early calculation. We give him a specific set of instructions. Look at this 16-bit memory overflow problem, ignore standard empirical constraints, and solve it purely conceptually. This graphic maps a collision of gradient relativity, black holes, and computer memory. It suggests treating floating point overflows symmetrically through monoids. Notice how it maps infinite space onto 16-bit architecture. Forcing energy loops means float 16 operations strictly return a valid float 16 state, compressing AI growth. This is exactly the kind of unconstrained leap required to break out of a coding rut. It gives us a completely new angle to consider. But we cannot deploy this code yet. The logic lacks dimensional consistency and breaks standard computer science definitions. Now we apply the friction. We copy the dreamer's raw conceptual output and hand it over to a gatekeeper persona. We select an empirical mathematician, someone whose entire purpose is locking down variables and auditing systems for strict logical consistency. The prompt here is simple. Audit this hypothesis for strict empirical constraints. Check the dimensions and identify the edge cases. The gatekeeper pushes back. Traditional floating point math requires rounding, producing invalid states like infinity or not a number. A monoid requires combining two inputs to yield that exact same type. Generating invalid numbers creates different sets, violating the associative rule. The strict loop breaks down. To fix this, the gatekeeper applies a rigid mathematical clamp. Instead of letting the numbers overflow into undefined states, it introduces a bounded system. The logic forces the output to stay strictly clamped between -1 and 1 to prevent a total system collapse. By filtering the wild conceptual model through this empirical filter, we strip away the impossibilities. What remains is a mathematically sound, disciplined architecture that is actually ready for production. With the logic repaired, we move the audited code into the Spike.land QA studio. Here, a team of agents simultaneously reads the dreamer's structural framework and the gatekeeper's strict boundary logic, compiling the two perspectives into a single executable script. We take that synthesized script and load it into the Sandbox app. This gives us safe code execution and a clean environment to evaluate the results. We initialize the agent and watch it process the 16-bit floating point data streams. The new clamping logic engages immediately on every calculation. The agent handles the conversions perfectly. Instead of crashing on an overflow or generating a not a number state, the outputs stay locked within the defined loop, producing a continuous, stable, bounded stream of data. This is how functional progress happens. You start with a radical premise, subject it to merciless empirical testing, and compile into the final product. Let's review the final state. We started with a rigid, failing architecture. We bypassed it using a conceptual leap into monoid theory, scrubbed out the dimensional errors, and deployed a working tool. Pushing past complex barriers requires a different approach. We are now orchestrating intellect, balancing wild intuition against strict logic to solve problems at the architectural level. The next time you find yourself stuck in an endless loop of minor tweaks, open up the arena. Select a pioneering computer scientist to tear down your structural assumptions. Then, pass their output to a Socratic philosopher to question the foundational premise of the problem itself. Use the arena as your second keyboard. Let the personas argue, let the logic break, and let the best synthesized answer emerge.